Okay, good morning, everyone. So last time we had just started talking about the Born approximation. Okay, and the Born approximation is an approximation for the scattering amplitude. Which looks like the following. The scattering amplitude as a function of the angle at which things are scattered is going to be given by a minus sign, which really doesn't matter at this point, times the mass of the particle over 2 pi h bar squared. And then you have to do an integral. In principle, this is an integral over all space. And what you integrate is e to the I k minus k prime dotted into r multiplied by the potential that's doing the scattering. Okay, and recall that k, we've decided we're going to take in the z hat direction. That's for the incident beam of particles. We send them in along the z direction, and then k prime is the waves that are coming out of the target, and we're very far away from the target. So to us, they're moving in the radial direction. Okay, so this is for the outgoing scattered particles. Okay, and both of them have the same magnitude. So the energy of these before and after scattering is h bar squared k squared over 2m. And then what we're going to do with this is we're going to square it, because squaring it gives us the differential cross-section, which is something we can measure. And so when an experimentalist does a scattering experiment, a lot of times that's what they're going to report to you in one form or another, is they're going to tell you what they got for the scattering amplitude. Okay, so we're going to do some examples of this, or at least a couple of examples. And so one important special case, you'll also get to do an example for homework. In fact, all the examples we will do will have this special case, is what happens if you have a spherically symmetric potential. Okay, and so that means our v as a function of r is actually only a function of the radial coordinate. And so in that case, the symmetry is azimuthal symmetry. In other words, if your beam is going in the z hat direction, you can rotate around the z hat direction and everything looks the same. And therefore, our scattering amplitude, which could have been a function of theta and phi, only depends on theta. And not only does it only depend on theta, it only depends on theta and a combination of the energy, because it only depends on Q. And the magnitude of Q is the magnitude of K minus K prime. Right? So Q is just this thing that's appearing up here in the exponent. Okay, and that Q, let's draw a picture of where these vectors look like. There's K, let's say, and there's K prime in the radial direction. And so Q is this vector. And if we call that scattering angle theta, then we can draw a perpendicular line, let's say like this, from this point perpendicular to the Q line. Okay, and so if we just redraw that triangle, That's a right triangle. This is supposed to be a right angle. And this angle is theta over 2. And this is q over 2. And this side here is k. And so q, the magnitude of q, is just equal to 2 times k times the sine of theta over 2, just from geometry. So when we compute this differential cross-section, if it's a spherically symmetric potential, that's the only combination it can depend on, because that's the magnitude of this. And there's no dependence on angles because this is spherically symmetric. Okay, and so now we can rewrite our scattering amplitude. Since it doesn't depend on phi, I'm just going to write it as a function of the one angle theta. And it's going to be minus m over 2 pi h bar squared. And so let me just rewrite the integral we're supposed to do here. So we're supposed to integrate over our potential, which really only depends on the magnitude. And then we have the exponential factor, which looks like this, e to the I q r prime. And then there's a dot product. The dot product is telling us that it's the magnitude of the vectors multiplied by the cosine of the angle between them. Okay, so that's the integral we're supposed to do. And now we can write this in spherical coordinates. This is integral 0 to infinity dr r squared. I guess I was putting a prime on here. It doesn't actually matter whether we call it primed or not. Actually, let me go ahead and remove all the primes. All they do is make things look ugly. So let's remove all the primes. Okay, so this is an integral dr r squared, and then an integral 0 to 2 pi d phi, and then an integral minus 1 to 1 d cosine theta. Okay, so as usual, the phi integral is the easy part. That just gives us a 2 pi factor. And now we can do this integral pretty easily. So we do this one first, because we're just integrating an exponential in cosine theta with respect to cosine theta. Okay, so this becomes minus m over h bar squared. The 2 pi's cancel. And then there's integral 0 to infinity dr vr over iqr times e to the iqr minus e to the minus iqr from doing the integral. And let's see, I forgot my r squared here. So I'll put it back. I'll squeeze it in there. Okay. And now e to the iqr minus e to the minus iqr over I is related to the sine of qr. So this is equal to fk of theta is equal to minus 2m over h bar squared. There's a factor of 1 over q. And then there's an integral 0 to infinity r times v of r times sine qr dr. Okay, so we've boiled everything down to doing a nice simple integral, or relatively simple integral. And so as a reminder, this is the Born approximation. It's not the exact thing. And it's in the case of a spherically symmetric potential. So if I were to give you a non-spherically symmetric potential, you can't use that formula. You have to go back up to this one, which is unfortunately much uglier. Okay, any questions so far on what we're doing here? Okay, so let's do a classic example that's actually quite useful. And this is called the Yukawa potential. And so in the Yukawa potential, this is going to be spherically symmetric. And it's going to involve two parameters. One of them is just a overall factor that we're going to call g. And then there's an exponential of minus r over a. A is some distance scale or some length. And then we're going to divide by r. Okay, so for small r, what does this thing look like? What do we mean by small? First of all, we mean small compared to the other length scale in the potential, which is a. Then it's going to be the same as a Coulomb potential, which we talked about classically for Rutherford scattering. And so to compare with Rutherford scattering, we would take our factor of g and call it the atomic number of the atom that we're scattering off of times e squared, the charge of the electron squared. On the other hand, for large r, then the potential goes to 0 because of the exponential. And so from that, we can sort of say that A is the range of the potential. Because we remember from when we talked about the classical Rutherford scattering, that if it were really exactly Coulomb, this thing would have an infinite range, meaning when we calculate the cross-section, it actually turns out to be infinity. But it's going to be a finite cross-section in this case, just because of the factor A there, which is sort of cutting off the potential at a certain distance. Okay, so Coulomb is Yukawa with the range A taken to infinity. Now, it turns out the Yukawa potential is, in quantum mechanics, very tricky. We're not going to go into all the subtleties of that, but you should be aware that actually this is a little bit glib to just say that the Coulomb potential is the A goes to 0 limit of the Yukawa potential. But on the other hand, in many real life problems, it turns out to be a good approximation, because in many real life situations, the Coulomb potential for an atom, let's say, is actually screened at large distances. Okay, so anyway, let's just plug that in and see what we get. So here's our scattering amplitude. The Born approximation just tells us to do an integral. Sorry, this is minus 2m over h bar squared, 1 over q. And then we're going to integrate our potential. Okay, and then there's a 1 over r in the potential, but there's an r in the integral, so they cancel nicely. And then the other thing we have to include here is the sine qr. Okay, and so that's a nice integral that turns out can be done very easily. This is, or looked up very easily. This turns out to be minus 2mg over h bar squared, 1 over q squared plus 1 over a squared. So q is something like a wave number. It has units of 1 over distance. And so the units make sense there. And as a reminder, q squared is 4k squared sine squared theta over 2, which we can also write as 2k squared, 1 minus cosine theta. That's a trig identity. And so remember what we're supposed to do with this to get the cross section is just square it. So the differential cross section is this thing squared. And so the 2mg gets squared. The minus sign goes away. And then what's left here is 2k squared, 1 minus cosine theta, plus 1 over the range, 1 over a, all of that squared. Okay, and so that's the result for scattering from a Yukawa potential. Again, this is the Born approximation. It's not the exact result. Okay, but now that we've got it, we can go ahead and see what happens in the a goes to infinity limit. So we're going to take a goes to infinity. And we might as well plug in that case, that g is ze squared to make it look like the Rutherford scattering case. And then we just get d sigma by d omega is 4m squared z squared e to the fourth over h bar to the fourth. And then the second factor there is just going to be 4k squared sine squared theta over 2. Sorry, sine to the fourth of theta over 2. Or actually, let me do it this way. Let's put the whole thing squared. That's what it's supposed to be. Okay, and then if you plug in what k is in terms of the energy, this is z squared e to the fourth over 16, energy to the squared sine to the fourth theta over 2. Okay, so there we've used that the energy is h bar squared k squared over 2m, just to write things in terms of the energy. And so what has happened here is that even though we were doing this in quantum mechanics, we got exactly the same as the classical Rutherford scattering. So the Born approximation does this quite a lot. The Born approximation is a semi-classical version of the complete calculation. It comes about from basically assuming that the potential is very weak, and so you're not getting interference between the different waves. Okay, so this is nice because we started with a potential that in a certain limit looked like the Coulomb potential. Then we did the Born approximation, we got an answer, and sure enough, in the limit where it was supposed to look like the Coulomb approximation, we got just that. Okay, so in a little bit, we'll talk about how to go beyond the Born approximation and get a more accurate answer that includes more the quantum effects. But let's make a bunch of comments, first of all, on the Born approximation in general. Okay, so one is, actually, let's make these comments about the spherically symmetric case, because that's the case that will arise the most. So for spherically symmetric, okay, so one thing is we can go back up to our formula here. And so we notice that even though the general formula was complex, this thing is always real. So no matter what the potential is that we plug in there, we do this integral, it's just manifestly a real number. There's nothing complex about it. Okay, so that's one thing, is that this is always real. And a second thing is that it's always linear in the potential. So if I make the potential twice as strong, my scattering amplitude will get twice as large, and then my cross-section will go up by a factor of 4. So my differential cross-section, which is always this, the square of the scattering amplitude, not only will it obey that proportionality, but it doesn't care what the sign of the potential is either. So this is independent of sign. Okay, and so for example, in the Rutherford scattering case, it doesn't care whether I'm scattering off a positive charge or a negative charge. So for example, the charges in Rutherford scattering, it only cares what the magnitude of the charges is. And so therefore, this is saying within the Born approximation, you can't tell the difference between an attractive potential and a repulsive potential. They give the same scattering. If they have the same strength, they give the same scattering, regardless of whether they're attractive or repulsive. Okay, here's another comment. We've really already said this one. Fk of theta, the scattering amplitude, and therefore the differential cross-section only depend on the energy and the angle through one combination. So only depend on q squared, which we can write as 4k squared sine squared theta, or sine theta over 2. Oops. So what that means is if we know the dependence on the angle, we also should know the dependence on the energy. All right, here's another factoid. So what happens in the low energy limit? So for low energy limit, that means k is going to 0, the wave number. And if k is going to 0, that means q is going to 0. And that's telling us that it can't depend on the angle theta. So in fact, if you go back and plug into the integral, f of theta is approximately, in that limit, minus m over 2 pi h bar squared. Okay, the exponential just goes away. And we're just doing this. In fact, this doesn't care if it's spherically symmetric or not. Right, so that's just some integral, but it doesn't depend on the angle. In our case, it's just this integral. Okay, and so this does not depend on theta. Okay, so low energy scattering in the Born approximation just gives you a constant differential cross-section. And that's the same thing we found classically for hard sphere scattering. When you scatter off a bowling ball, the probability to go off in different directions is constant. So that's the low energy limit. And now you can ask about the high energy limit. The high energy limit is going to be large Q. Although this applies not just to high energy, but to any large Q. And so for large, so it won't apply, for example, in the high energy limit if you happen to make sine theta be small. So anyway, for large Q, high energy limit, as long as theta is not too small, then this should have been fk of theta, then fk of theta is going to go to 0. And the reason it's going to go to 0 So I'll just write goes to 0. It's because of the oscillation of the integrand. And specifically, there's a factor of sine QR. Okay, and if Q is very large, let's go back up to the formula. Way back up here. If Q is very large, then this sine function is oscillating up and down really fast as we vary R. And so if V of R is something reasonably smooth and not too contrived, this is just going to average to 0. And so the scattering amplitude will go to 0, and so the scattering cross-section will also go to 0. Okay, so that tells you that actually the Born approximation is at high energies better than you have a right to expect it to be, because it's going to give a small cross-section, which is self-consistent with the Born approximation that you can neglect the scattered wave. More generally, you can ask, when is this Born approximation valid? And remember what the Born approximation was we assumed that the whole scattering wave function within the target is not too different from the incident beam, which was e to the I k dot r over 2 pi to the 3 halves. Okay, and so that's what you need for the correction term that we didn't include to be small. And shortly we'll talk about what happens when you go beyond that approximation. But right now for the Born approximation, what does that mean? It means if I do the correction term in magnitude, so I'm forgetting about the minus sign, and so it looks something like this. And I'm just going to write e to the I q dot r over r times v over r prime. Okay, that should be much, much less than 1. And so for any given potential, you can check this on a case-by-case basis. Okay, but for the same reason that the cross-section got small, this is probably going to be better at high energies. Okay, so so one thing is if the potential is small, then that will be certainly small. So that's one limit in which it should work. And for higher energies, which means large Q, then the e to the I q dot r is sines and cosines, and those will oscillate more and you'll get more cancellation. So the Born gets better and better because the integrand oscillates. It's at low energies that you usually have to worry. So let's think about this just in the Yukawa potential case that we just did. Let's worry about the low energy limit of the Yukawa potential. So at low energies, in the Yukawa potential case, so there's the e to the I, let me call it Q again, because it's k minus k prime, so that's Q dot R. So we can just take that to be 1. That's the worst case scenario. And 1 over r within the potential is greater than about 1 over a as a crude approximation, because when you get farther away than a, the exponential is killing the potential. So this is the region where the potential is non-zero. Okay, and so as a very crude approximation to what's going on with this integral, you can just multiply the value of the potential at r less than a by the volume of it. And so what you get is approximately 2m, the absolute value of g. Remember, it doesn't care what the sign of g is, times a over h bar squared has to be much, much less than 1. Okay, so you can either do that by making the overall factor of g to be small, or you can make the a factor small compared to the mass over h bar squared. Okay, so this is the condition, the very rough condition for the Born approximation to be good, if that's satisfied. And so you can compare this to a different condition, namely the condition to have a bound state for the same potential. So you may recall that in 3 dimensions, as opposed to 1 dimension, potentials don't always have any bound states. You have to have the potential be strong enough in order to have a bound state. So the condition necessary for a bound state to exist turns out to be that 2m times the absolute value of g times a over h bar squared has to be greater than about 2.7. So the really important thing is just that it's a number of order 1. You can get this by, for example, estimating the ground state energy with the variational principle. Just throw in your favorite wave function that approximates it, figure out what the energy has to be from that. Okay, and so that's roughly what you get. And so you can see that the Born is good approximation is the complement, basically, of the bound state exists condition. Or another way of saying it is, if your potential is strong enough to have a bound state, then you shouldn't expect the Born approximation to work at low energies. So if a bound state exists, then Born approximation is going to fail at low energies. It may still work at high energies, and so you may still be okay. But at low energies, it will fail. All right, any questions about that? All right, so I promised to say what will happen if you go beyond the Born approximation. And so there are different ways to approach that. One is to just sort of abandon the Born approximation completely and do something else. And we'll also do that. But let's see if we can make a series that will give the Born approximation as the first part, and we'll have corrections to it. So this is the Born approximation beyond leading order. And really what that means is, instead of just keeping things linear in the potential, now we're going to keep things quadratic in the potential. Okay, so how are we going to do this? We're going to do this in a slightly roundabout way by going back to the Lippmann-Schwinger equation. And so the first thing we're going to do is we're going to define something called the transition operator. not to be confused with the translation operator. The symbol isn't unfortunately similar because they both start with T, but we're going to define the transition operator T such that when it acts on any plane wave state, K, so that's some momentum eigenstate, that it gives back the potential that we're talking about times the resulting scattering state, which we called psi plus or minus, but now we know it's psi plus. Okay, so that's how we define it for every plane wave. Okay, so T acting on a plane wave ket gives you back the potential times the resulting scattering state. So it's not obvious maybe right away why this would be a good thing to do, but now we can plug into Lippmann-Schwinger to see what happens. Okay, and so we've got T acting on K is equal to V acting on psi plus, but Lippmann-Schwinger tells us psi plus is our plane wave plus the result of the scattering, which looked like this. 1 over E minus the free Hamiltonian plus I epsilon. At the time we wrote it down, we said plus or minus, but now we know it's plus. And then here we have V again times psi plus. Okay, so that's what Lippmann-Schwinger tells us. But now if we stare at that, we realize we have V times psi plus, which we can write again in terms of T times K. So let's go ahead and do that. We get T times K is equal to V plus V times 1 over E minus H0 plus I epsilon times T. And now everything on the right side is a K, is our plane wave state. So now we've got a great equation because both sides just have K in them. And this was supposed to be true for every, by definition, for every plane wave ket. And if an operator acts on every state in a basis and obeys some condition, then it basically is always true. Okay, so since true for every plane wave ket, okay, and that's an ortho basis, then by linearity, we just have the operator equation is true, that T equals V plus V, 1, we have this funny inverse operator times T again. Okay, so that's an operator equation. We wouldn't be able to do that if this were just true for some states, right? Because if it's just true for some states, then as an operator, it might be only true because of the special properties of those states. It's the fact that it's true for every state in an ortho basis that means we can just sort of cancel these off. Okay, so anyway, we have this operator equation, and we can now solve for the operator T. And we do that first by bringing T to one side of the equation, and then dividing by the appropriate inverse operator, which turns out to be this. So T is 1 minus V times this inverse operator. And then we have to take the inverse of that multiplied by V. So this is a funny equation because it involves the inverse of an operator that involves an inverse. But now we can simplify it a little bit by using the fact that when you have an inverse of 1 plus or minus something, that's not too bad. So if we have 1 minus x inverse, that has a series expansion, which is 1 plus x squared plus x cubed forever and ever. Okay, and so now we've got that our transition operator is v. The next term is v times 1 over e minus h0 plus I epsilon times v. And the next term in the series, basically every term in the series looks like powers of the inverse operator with v's sandwiched in. Okay, and so now we've basically solved for t, the transition operator, in terms of the given potential and the energy that we're scattering and the free Hamiltonian. Okay, so now we have to contemplate, why is this useful? So recall that our scattering amplitude is minus 4 pi squared m over h bar squared times this matrix element. Okay, that wasn't the Born approximation, that was the exact thing. But now v times psi plus, by our definition, is the transition operator times a plane wave. Okay, and so now, just rewriting this, we've got the scattering amplitude in principle in terms of only things that we actually know. Okay, we've got the final state plane wave. We've got the transition operator, okay, which is up here, known as an infinite series. Okay, and then k again. So up to the fact that we've only got it as an infinite series, which has to be summed, and you have to worry about convergence and things like that. But up to that, we've got the final scattering amplitude completely known, or known in terms of known things. Okay, and so in particular, because this is an infinite series, we can write this thing as an infinite series. So we can write this as, first of all, f1 k of theta and phi plus f2 k theta and phi plus going on forever. And the number up top, so 1 means that you have one potential in it, and 2 means you have two potentials, right? That will be this term. And the fk3 will have 3 potentials. That will be this term. Okay, and so in fact, now we can write down what each one of those is. f1 k theta and phi is equal to, this is what we've been calling the Born approximation. Okay, it's k prime vk, which we wrote in position space before, but it's the same thing. So this is the Born approximation, or sometimes it's called the first order Born approximation. It's what we've been calling the Born approximation. Okay, and so all that is saying, to first approximation, the transition operator is the same thing as the potential, which is saying that we're not including higher order effects. Okay, but now if we want to go beyond, we just need fk of 2, which is going to be the same thing almost, except now the operator that goes in there is this thing. And so we somehow need to evaluate that. And let's say we wanted to get really ambitious and go to third order, which we will not do in any examples. Okay, it's the same factor out front. But now we just have a harder matrix element to evaluate, which is going to have 3 potentials in it. So when we go to position space to evaluate this thing, it'll just be a harder integral. And there should be a prime right there. Okay, so now you can evaluate these in position space, just like we did for the first order Born approximation. And the same thing will happen, which is we'll get things involving the green function. So for example, F2k of theta and phi is minus 4 pi squared m over h bar squared. Now, instead of one integral, like in the Born approximation, there are going to be 2 integrals. And it turns out there's a factor e to the minus I k prime dot r prime potential. This is just translating the formula above into position space. The inverse operator becomes our green function. And we get our 2 potentials, and then we get e to the I k dot r double prime. Okay, so you have to evaluate that integral, which is a little bit hard because the green function might not be so easy to include. But in principle, that's a doable integral. You can have your computer do it for you. And then you can do a similar thing for this. This is going to involve 3 potentials and 2 green functions and some exponentials. So you can draw a pictorial interpretation of all of these formulas, which is given a little bit more precisely in the notes, but I'm just going to sort of sketch what happens here. So if I draw my potential as some shaded region, and then I have my beam coming in, the first Born approximation is I just do an integral over that potential to get my k prime coming out. Okay, this is F1. And then the second Born approximation contribution, I come in, I scatter once off the potential, I scatter twice off the potential, and then I go out. Okay, and so this is my r prime, and this is my r double prime that I have to integrate over. And then if I were to do the third Born approximation, I come in, scatter once off the potential, scatter again, scatter a third time, and then I get to leave. Okay, and you can turn those pictures into formulas. Each dot that I've drawn in here is an interaction with the potential. Okay, and in between, I draw lines with arrows. This corresponds to the propagation of the particle as if it were free, because it's not interacting with the potential. For initial lines, I always put a factor of e to the I k dot r. For the final line, I put e to the minus I k prime dot r. And then for any internal line, I put a green function. So that's really a factor of 2 pi over h bar squared times the green function between the 2 points that I'm integrating over. So I can call them R1 and R2, like so. Okay, so to represent this, the total scattering amplitude, I draw all possible pictures. For each dot in the picture, I put in a potential. For each line in the potential, or each line in the figure, I put in a factor like that. And then I integrate over all positions where I could interact with the potential. That's basically what this is doing. And add up all those things, and in principle, that gives me the exact scattering amplitude. If I could somehow do this, summing up every possible picture in this way. Okay, so that's the Born series. That's the Born approximation taken beyond leading order. All right, so that's it for today. Next time we will go on to talk about other ways of evaluating scattering amplitudes, which don't necessarily involve the Born series. Okay, any questions on today's lecture? All right, then if not, I will see you all on Wednesday.